You know, we spend a lot of time trying to predict the physical world around us. How does air flow over a new jet wing? How will a new medicine actually mix inside our bloodstream? Getting these things right, well, it's the foundation of pretty much every major industry. But what if I told you that our very best tools for the job are starting to hit a major wall? Let's dig into why, and how a totally new kind of AI might just be the breakthrough we need.
So simulating how things like air and water move, it's a whole field called computational fluid dynamics, or CFD, is absolutely mission critical. I mean, it's this invisible science that lets us design more efficient engines, build faster cars, and even create life-saving drugs. So much of our modern world really depends on it.
But here's the catch. The methods we've been using, while they're incredibly powerful, are starting to show their age. There's this fundamental bottleneck that costs a fortune in both time and money, and it's really slowing down the pace of innovation. So it makes you wonder, right? There's got to be a better way.
All right, so first, let's really get our heads around the problem we're trying to solve here. Why is it so incredibly hard for even our best supercomputers to simulate something that sounds simple, like water just flowing through a pipe?
Okay, so the standard tools, they work by taking a shape and just breaking it down into millions of tiny little cells. Think of it like a super detailed digital mesh. Then they solve the physics for every single cell, one by one. It's accurate, for sure, but it's a total brute force approach. And here's the real kicker. If you want to change the shape even a tiny bit, like, I don't know, tweak the angle of a pipe, you have to throw the entire simulation out and start all over again from scratch. It is an unbelievably slow and expensive way to do things.
This is where our story takes a really fascinating turn. Instead of just trying to force the problem with more computing power, some researchers asked a much more interesting question. What if? What if we could teach an AI to actually understand the physics itself?
And that brings us to this, the Physics-Informed Neural Network, or PIN for short. Now, this is not your typical AI. The best way to think about it is like a brilliant student in a physics class who can't just guess the answer. They have to show their work. A PIN is literally forced to make sure its predictions obey the fundamental laws of nature, like the famous Navier-Stokes equations that govern how fluids flow. So its answers don't just look right, they actually have to be physically possible.
So how does it pull this off? Well, the process is actually really elegant. First, you just feed the PIN a set of coordinates in space. The AI then makes a guess, a prediction for the fluid's velocity and pressure right at that point. But here's the magic trick. Its prediction is immediately checked against the laws of physics. If the answer breaks those laws, even a little, it creates an error. And the AI's one and only goal is to tweak its own internal brain to get that error as close to zero as it possibly can. It literally learns physics by constantly trying not to break the rules.
And that right there is the massive advantage. The traditional solver, it's like the tortoise. It's slow, it's steady, but it has to start the entire race over from the beginning every single time. The PIN is completely different. Once it learns the physics for one shape, it can use that knowledge, it's a process called transfer learning, to very quickly solve a brand new one. There's no starting from scratch. It's just a much, much smarter and more flexible way to work.
And you know what? For a simple test case, it worked beautifully. On the left, you're seeing the result from a traditional solver for fluid flowing around a cylinder. And on the right, that's the PIN's prediction. They're almost identical. In fact, the research paper this is all based on found that the PIN's prediction for velocity had a relative error of just 1.2%. I mean, that's tiny, a huge success, right? But what happens when things get a little more complicated?
Of course, every great story needs a little conflict, and just when it seemed like this new AI was the perfect solution to everything, it ran headfirst into a problem that it just could not solve by itself.
This quote from the research paper, it really says it all. When the researchers moved on from a simple cylinder to a much more complex, Y-shaped mixer, something went terribly wrong. The AI's solution simply faded away. As they put it, it degenerated to zero. You can see the failure happening right here. The AI starts out great. It correctly predicts the flow going into the mixer, but as the fluid moves downstream, the prediction just dies. It completely flatlines. And this is a catastrophic failure. It violates the basic law of conservation of mass. I mean, you have fluid flowing in, but the AI is saying nothing is flowing out. The AI just got lost in the complexity. Technically, it's a problem called gradient vanishing, which basically means the AI lost its way and had no idea how to improve itself. Its classical mind had hit a brick wall.
But what if you could give that AI a completely new kind of brain? Something that was capable of seeing patterns and complexities that a classical computer just can't. Well, this is where the researchers had their big aha moment.
Their solution was this thing right here. the hybrid quantum pin. Now, instead of just replacing the classical AI, they gave it a partner. They inserted what's called a quantum layer, which is essentially a small quantum processor that works right alongside the classical network. It creates a true hybrid brain, one that combines the absolute best of both classical and quantum computing.
Now, the huge benefit of adding this quantum layer is a concept called expressiveness. And put simply, it just gives the AI a much richer vocabulary to describe the world. It can learn and represent far more intricate and complex solutions than a purely classical network could ever hope to. It's kind of like giving an artist a whole new palette of colors to paint with, allowing them to capture all these new subtleties they couldn't see before.
Okay, so the theory is fantastic, but does it actually work? The researchers decided to find out. They put the classical AI and the new quantum hybrid AI in a direct head-to-head competition on the exact same complex problem that made the original AI fail so badly.
And the result? This number, 21%.
What is that? That is the measurable improvement in physical accuracy. By adding that one quantum layer, the hybrid model produced a solution that was 21% closer to reality, 21% better at obeying the laws of physics than its purely classical cousin. It didn't get lost, it didn't fail, it found a better solution. And this graph right here is all the proof you need. The vertical axis, that's the error. It's how much the AI's prediction violates the laws of physics, so lower is better. The green line is the classical AI, and you can see its error is higher. But the blue line, that's the hybrid quantum model. It consistently gets a lower error, which means it found a more physically accurate solution to this incredibly complex problem. The quantum boost actually worked.
So this is way more than just a cool experiment in a lab. It really represents a whole new way of thinking about how to solve some of our toughest engineering challenges, and it could seriously accelerate innovation across the board.
So why does all this matter to you and me? Well, it means we can potentially design more aerodynamic cars and planes faster and more accurately than ever before. It could speed up the development of new drugs by simulating how they behave with incredible precision. It could help us create more efficient chemical mixers, saving tons of energy and resources. By smashing through the limitations of classical AI, this hybrid approach is opening the door to solving a whole class of problems that, until now, were basically out of reach.
And that really leaves us with one final fascinating question. In this explainer, we saw how a quantum boost helps solve the incredibly complex problem of fluid dynamics. But what's next? What other monumental challenges out there, in science, in finance, in medicine, are just sitting there waiting for a hybrid quantum brain to come along and finally crack them wide open? The possibilities? Well, they're just starting to unfold.